All right, so everybody remember please to sign in. Don't want to forget anybody. And we will continue with counting here in a minute or so, once everyone has had a chance to log in and get set up. Okay, all right. So happy Monday, welcome back. So we have been talking about this idea of counting. The main concept is trying to see counting possibilities, whether it's different possible passwords or different outcomes from dice rolls. This is what we're talking about with counting. So one example that I wanted to come back to was the top one here. A 2-digit code is constructed using digits 1 through 4. If the second digit is required to be at least as large as the first digit, then how many such codes are possible? So this one was a little bit different from the other ones that we had been working with. But starting, I guess, kind of from the simplest possible terms, how would we figure out how many different two-digit codes we can make from the numbers 1 through 4? Just start with that question. How many 2-digit codes can we make with the numbers 1 through 4? So the first question is, how many characters or how many events are there that can happen? So it's a 2-digit code. So the code is going to have 2 slots. There's 2 events, 2 things that need to happen. Okay? So starting off with the simple version, using the digits 1 through 4, how many total possibilities are there? How do we figure out how many possibilities there are?
Don't you have to go through each one of them?
I'm sorry?
You have to go through each one of them, right?
Yeah,
Like possibilities or something?
yeah. So each one has how many possibilities? How many options do you have for the first digit?
You say two?
I'm sorry?
Two, one, two, like nine?
Yeah, because it could be 1, 2, 3, or 4.
Nine?
So 4. How many possibilities for the second option?
Nine again?
I'm sorry?
Is it nine again?
I can't hear you.
Was it nine again?
No, because we're only using 1 through 4.
Oh, well, three.
It's just 4. We're doing a simplified version of the question.
Oh,
So
okay, okay.
how many total versions are there of this code?
Only one?
Well, no. So you take the number of possibilities of each place and you multiply them. So in this, it's just 4 times 4 equals
16.
16. All right. So yeah, 4 times 4 equals 16. But this has a slightly different extra bit to it. It says the second digit is required to be at least as big as the first digit. So this one is helpful if we plot it out kind of graphically. So let's look at all of these initial combinations. We have the first digit and the second digit. So we have 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2. All right. So the second digit needs to be at least as big as the first one. So let's see which ones of these, all these 16 combinations goes away. So you can kind of think about this as a table of different combinations. Well, in this first column, this digit is at least as big as this one. And the rest of them, the second digit is bigger. So in this one, this digit doesn't work, or this value doesn't work because this one is not as big. So we lose that one. But this one, and this one are all still correct. Now let's look at this. This one goes away, and this one goes away. But these two still work. And then over here, this one, and this one all go away, and that one works. So, how many possibilities are left? How many did we take away?
We took away 7 possibilities.
We took away
Let's see.
6. 1, 2, 3, 4, 5, 6. So 10. So you can make 10 codes with this setup. So this is an example of a rule that you'll kind of have to think about a little bit. But there's a few ways you can kind of consider it. One is writing them out like this and just taking away the ones that don't work. Or you could think about how it's laid out. So all the ones on the diagonal are fine, and there's 4 along there. And so the other halves have to be split between, you have 12 left, so you have 6 on this side, 6 on this side. If it was the other way around, where the second digit has to be less than or equal to, then this side would be fine, and this side would go away. So there still would be 10. It's just something that you kind of have to put a little bit of thought into. What does that rule actually mean? So when you see it, take a step back and consider it for a second. So let's continue on. Let's see. All right. So in the previous examples and this one, when we are reducing the number by 1 each time, sometimes call this a permutation. This word may show up in your homework. Example, how many ways can we arrange the digits 1, 2, 3, 4, 5? The original value is counted also. Note that this value is called a factorial. Okay? So we're trying to figure out how many different ways can we arrange the numbers 1, 2, 3, 4, and 5. Okay? So how many different events or digits or places are there going to be in this thing? So on the board, when I draw the little dashed line on this last one, and I said, how many digits for the code are there? There was 2. Well, how many digits are there in this one? So how many digits is this number, or are all these numbers going to have?
Is it 5?
5, yeah. So we're arranging the numbers 1 through 5. And so there's going to be 5 different place values. Okay? So how many possibilities are there for the first spot? How many different things can you put in that first one?
5.
5. Yeah, because you could put 1, 2, 3, 4, or 5. Okay? What about the second spot?
4,
4. Why 4?
because you just put a number in the first spot.
Exactly, because I just used one of them. Now, it doesn't matter which one I actually used, but I definitely used one of them. So that's exactly right. So we have 4 possibilities for that section. I'm having some internet issues. What about the next section? How many options do I have for that one?
3,
3. Yeah, for the same reason. I've already used 2 of my 5. What about the next one?
2,
2 and 1.
1.
Yeah. So in total, how many options do I have?
Is it 5? Or you adding them?
So you have to multiply them.
Is it 120?
Okay.
Yeah, it's 120. So a quick way you can do that is, what is 2 times 5?
10,
10. What's 4 times 3?
12.
12. So you have 12 times 10 is exactly right, 120. So this comes up a lot in math. And this multiplying all of the numbers from some number down to 1 in a row like this is called a factorial. And it has a notation that looks like this. You put the first number you start with, and then you put an exclamation point. So factorial 5 means 5 times 4 times 3 times 2 times 1. You can have factorial 10, which is 10 times 9 times 8, 7, 6, 5, 4, 3, 2, no. Okay, so factorials are something that gets really, really big very, very quickly. But it's also, just kind of by definition, it is how to arrange that many different things. So if you're talking about in a class, how many ways can you arrange 10 different students in a line? It's 10 factorial. How many different ways can you arrange 10 distinct or any number of distinct objects? It's that number factorial. And this number grows very, very large, very, very quickly. So just for some examples, 3 students out of, let's say, 25 in this class are needed to fill special positions. So let's say out of 10. So 3 students out of 10 need to fill special positions in the class. Let's say teacher's pet, the grade beggar, and that guy. So how many ways can they be chosen? So let's see. This one's a little bit different. So we have 10 students and 3 positions. Okay. So how many different ways could we fill that? So first off, how many spaces do I need?
3.
3, yep. Because there are 3 students, or I'm sorry, 3 positions. Now, how many options do I have for the first position?
10.
10. How many options would I have for the second position?
9.
9. And what about the third position?
8.
8. Yeah. So, very good. How many, does anybody happen to know how many this is?
720.
Woo. Yeah. And again, a quick way to do this one is, what is 9 times 8?
72 is add a 0.
Yeah, 72, and then exactly right, add a 0. Very good. Yeah, so we have 720. So this is the same kind of idea. It's starting with some number of numbers, but because you can't reuse anything, it's 10 times 9 times 8. Now, there is actually a way to write this in factorials, and it's pretty helpful. It even has a name. It's in choose K, and this probably won't be directly on a test, but not the in choose K part. But if you have n things, in this case, we have 10, and you need to choose K of them. In this point, or in this case, we chose 3 of them. Then in choose K is always in factorial over n minus K factorial. So this seems kind of random. But what does, in our case, what is in factorial? What is n for this problem?
10.
Is it the students?
It's 10. So in factorial is 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, 1. Okay. So what is n minus K?
7, huh?
Yeah, 7. So what is 7 factorial?
7 times 6 times 5 times 4.
So remember when we're multiplying fractions, what is 7 over 7?
Just 1.
6 over 6?
1.
1, 1, 1, 1, 1, 1. So n factorial over n minus k factorial just means n factorial down to n minus k. So in this case, it's 10 down to not to 7, but before 7. So this is the mathematically version of it, if that's the kind of thing you like. But if this is really weird and confusing, it's not quite necessary, but to me, it does clear things up a little bit. So let's look at it in a different context. So how about this second one? How many digit pens can be made from the standard 0 through 9 if no digit can be used twice? So, how many positions do I have?
Four, right?
4, yep, very good. And how many options do I have for the first position?
9.
Not 9.
None.
It's not 9. If you had the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, then there would be 9.
10.
10, yeah, because poor little 0 gets forgotten every time.
Oh, okay.
Yeah. So, first position, we have 10 options. What about the second position?
9.
That's where we've got 9. Then
8. Then 7.
yeah. So this turns out to be 540. But again, the exact answer isn't as important as the setup because you will be able to use calculator and stuff for this. So it's more important understanding how the setup works and not trying to memorize 10 times 9 times 8 times 7. But it's the number of positions or possible events. And in each position, you put the number of possibilities. And in these cases, since you can't repeat anything, it gets reduced by 1 every time. All right. So let's see. All right. So how about we do some similar exercises? How many 3-letter words can you make using the letters M-A-T-H? So how many possibilities are there? Or how many slots are there, I guess?
Is it 3?
Yep. So there's 3 slots because it's a 3-letter word. And how many options do we have for each letter? So this is why words is in quotes, because it doesn't have to be a word that makes sense. We just mean a word as in a combination of 3 letters. So how many options do you have for the first one? What?
4.
Yeah, because M-A-T or H. What about for the second one?
3.
So if we're not allowed to use any repeats, then it would be 3. But we didn't say that. So how many is it? Since we can have repeats.
4 again.
What? Sounded right, but just
4
want to.
again.
What'd you say?
Is it 4 again?
Yeah, it's 4 again, because we can use all 4 of them this time. So 4, 4, and what about the last one?
4.
4. Yeah. So in all cases, 4 times 4 times 4, which is 64. Okay. So B, number of ways that you can change a $1 bill with 5 nickels, 12 dimes, and 6 quarters. Do we know how to solve this using our counting rules? Say not really. So theoretically, you could just write out all the possibilities, but using the stuff that we've got, that extra little tidbit is very difficult to do. We don't know how to include the rule of all of these things has to equal $1, and it also doesn't tell us how many different slots there are. It doesn't say that you have to give back exactly 6 coins or something. So no, we can't really do B. We could do it the old-fashioned way, but that's not where we're at. So how about the number of ways that a 5-card hand can be drawn from a deck of cards? Can we solve that? So it doesn't tell us if we're talking about a specific 5-card hand, if we're talking about a generic 5-card hand. They're talking about like poker. So you could have 4 aces and a 2 or something. We don't really have enough information. We could say, you know, how many different possibilities could you have of a 5-card hand? That's a pretty interesting one. So let's do that. How many different 5-card hands could you get if you assume that the 2 of hearts and 2 of clubs is actually different? So how many cards are there in a deck? Does anybody know? What?
Is it 24? I don't even know.
So there's 4 suits, and there's 13 cards in each suit. So a suit is like hearts, diamonds, clubs, spades. So if there's 4 suits and 13 cards in a suit, what?
52.
52, yeah. And if anybody's ever had a really annoying sibling, if you're playing with cards, they'll come in and say, hey, let's play a game of 52 pickup, and then they just throw the cards through the room and make you go pick them up. Life is hard. So you have 52 options. Where are we at time? Yeah, we're probably about to leave. So a 5-card hand, 2, 3, 4, 5. So how many options do you have for the first card?
52.
52. And then you have how many for the second card?
51.
51. 50. 49. 48. So this is a very, very big number. It's part of why poker is so interesting. Because there are so many possible options. So this is 311 million 8